So we have a problem here that is asking us to find the equation of the tangent line of function f of x at points 1, comma negative 1, utilizing the limit definition of the derivative, which is shown below. Now, firstly, we need to plug in our f of x values into the limit definition of the derivative. So we can see that over here. And just double check that this makes sense. We're plugging in x plus h into all values of x for this first term in the numerator. So x plus h into this numerator in the x, and x plus h into this x in the denominator. And we're going to be doing the same thing with the second term of f of x, except we're just plugging in x into our function of f of x. So we're not changing anything. Now, for simplicity's sake, for rewriting this, let's let this entire numerator be a variable, alpha, in this case. And I'm doing this so I can show you an inequality that I will use later and you need to know. So we have so far that the limit as h approaches 0 of alpha, the derivative of f of x equals the limit as h approaches 0 of alpha over h. Now, this is the same thing as writing the limit as h approaches 0 of alpha over h over 1. Now, this is important because we can do a cool thing called just flipping it and multiplying it. And you can see that here. So this entire thing is equivalent to 1 over h times all of alpha. You can do a quick, just double check, think about it, make sure that makes sense. Okay. Now, our next goal is to simplify alpha. We set alpha to be this entire numerator. And the problem here is that alpha is split into two terms. We want alpha to be one singular term. However, I want you to just ponder really quick, maybe do some work, and think about how you could get all of alpha to be one term. So to combine this one and this one into one single thing. Get rid of the subtraction sign. Okay, so your next goal, or in order to achieve just getting it into one term, you would need to find a common denominator so you can combine these two. And a really easy way to do that with variables that you don't know the values of is simply multiplying the denominator of each variable by the denominator of one term by the other term. However, you do need to multiply also the top term's numerators by it as well. So because this is equivalent to all of this will be equivalent to 1, as you can see, because it's the same thing over the same thing. And it's the same property over here, where it's going to be the same thing over the same thing, which will also equal 1. And what this will do is it will get you x plus h minus 2 times x minus 2, and you get the same exact thing on both terms. Therefore, you can simply combine both of these terms into one singular term by combining the denominator, which is x minus 2 times x plus h minus 2, as we can see here. And then you'll simply have x minus 2 times x plus h, as we can see here, minus x times x plus h minus 2, as we can see here. Now, what I want you to do next, to do some more simplifying, is to distribute all of these values in the numerator only. So I'll give you a quick second to do all that. And just leave the denominator untouched for now. Okay, so you should have ended up with something like this. A whole bunch of random variables. However, what we can do here is we can realize that there are some like terms that we can cancel out here. Actually, quite a lot of like terms that we can cancel out. So if we just go ahead and do that over here, we have an x squared and a minus x squared. Cancel that out. We have an hx and a minus hx. We can go ahead and cancel that out. We have a minus 2x and a plus 2x. We can go ahead and cancel that out. And now we have just a stray negative 2h. So our function should look something like this. Now, this is as simple as we want to get it, because recall that we have that the derivative of f of x equals a limit as h approaches 0 of 1 over h times alpha. And if we go ahead and plug that back into the limit function, we'll get this, right? Just double check that makes sense really quick. Alpha is this, and we just plug that in. And we can see that in the numerator, each term, or the entire numerator, is being multiplied by an h variable, right? And we can also see that the entire denominator of this limit is also being multiplied by an h variable, which simply means that we can go ahead and cancel out this h variable, which will leave us with this, which will leave us with a function that if you plug in 0, it won't give you some indeterminate or undefined value. So after plugging in 0, we can see that we have x minus 2 times x plus 0 minus 2, or x minus 2, which means we can simplify this to negative 2. I brought the negative out in front, if you haven't realized. We'll have negative 2 over x minus 2 squared. And this is our final destination for the derivative of f of x. However, recall that we're trying to find the equation of the tangent line of f of x at points 1, negative 1. And this is our slope function, which means if we have a curve, whatever, in say this is 1, if we plug in 1 into f prime of x, that will give us the slope of this tangent line. So go ahead and take a second to plug in 1 into f prime of x in order to find the slope of the tangent line. So you're just substituting 1 into x here. And that should get you f of 1 equals negative 2. If you didn't get that, try to plug it into a calculator or something. And this will give you your m value, or your slope value, basically how steep your slope is. And you know that your x1 point will be 1, and you know that your y1 point will be -1. And now you know that your slope will be -2. So you have all the variables that you need in order to solve this equation. So you can just go ahead and plug in right now. I'll give you a couple seconds. And you should end up with y minus -1 equals -2 times x minus 1. And you can see the plugin for all those right there. And if you simplify, it'll just be y plus 1 equals -2 times x minus 1, which you can see here. If you plug it into Desmos, it does indeed give you a line that is tangent to your original curve. Voila.